Hello everyone. Welcome back to physics-based animation. In the last video, we took a whirlwind tour of time integration, and we used this knowledge to develop several simulations of our venerable 1D mass spring system. Well, after 2 whole lectures languishing in one dimension, it's time to take it up a notch. And enter the third dimension, where we'll learn to build simulations of springy 3D shapes, like the Stanford Bunny. Now, this is going to require us to pull together all the things we've learned from videos 1 and 2. So not only are we going to need our newly acquired knowledge of time integration, but the Euler-Lagrange equations are going to feature prominently as well. Now, it can be useful to revisit the previous 2 videos as necessary because these concepts are going to be important as we go along. There are links readily available in the descriptions of this video. Alright, let's get started. As is becoming the norm, we are going to walk before we run. Before we build an entire bunny, we'll look at a single spring again, but with some differences. First, we can see that unlike our previous 1D example, our spring will have particles at both endpoints. Most prominently, these particles will have positions in 3-dimensional space. So we've picked our mass spring example off the screen and moved it into the real world. Almost as important, our spring is now going to have a non-zero rest length, given by the value L0. This means our spring will attempt to maintain some separation between the 2 particles to which it is attached. Now let's take this new setup and work through building the associated equations of motion. To do this, we'll follow the exact same steps as we did for the 1D spring, starting with defining the generalized coordinates. Previously, the position of our only particle was used for the generalized coordinate. The configuration of our new 3-dimensional spring depends on the positions of both endpoints. So we choose both endpoints as the generalized coordinates and stack them into a single 6-dimensional vector Q. We will also need the generalized velocity of the system, which we get by taking the time derivative of the generalized coordinate. And from this, we can see that the generalized velocity is just the stacked 6-dimensional vector of particle velocities. As before, our goal is to build the Lagrangian for this system, which means we will need to take these generalized coordinates and velocities and synthesize kinetic and potential energy functions of our spring. Let's start with the kinetic energy. But first, a little refresher using our 1D spring. Remember that in 1D, our kinetic energy was the familiar form 1/2 mv squared. We can reimagine this as the Euclidean 2 norm squared of the 1D velocity, or said another way, the squared magnitude. Now, this is not particularly useful in 1D, since v is a scalar, and all this extra notation just sort of obfuscates things. However, this formulation, using the 2 norm, makes the kinetic energy formula immediately applicable to higher dimensional systems. One such system is our 3D spring. So here it is again. And remember that each particle attached to the spring has its own velocity, and the kinetic energy in the system is completely derived from these velocities. So okay, we can use our new kinetic energy formula to calculate the kinetic energy of each particle separately. But remember, we're after the kinetic energy of the whole system, and that includes both particles. So we have to add these values together. We can compactly express this summation by exploiting the fact that the squared magnitude of a vector can be expressed in terms of the dot product of that vector with itself. Next, we are going to introduce the per particle mass matrix, M sub I. This is just a 3x3 identity matrix multiplied by the mass of our particle. Finally, we're going to use our stacked velocity vector, q dot, to simplify things even further. we can see that this summation over particles has a compact form given by q dot transpose mq dot times 1/2, where m is now the block diagonal mass matrix for the entire physical system. In this case, with two particles, this is a 6x6 matrix with 3x3 particle mass matrix blocks on the diagonal. Using this mass matrix, the kinetic energy for our single 3D mass spring system can be written compactly as a quadratic function of q dot. Okay, not so bad, right? We're done with the kinetic energy. Sure, it was a little more involved than the 1D case, but arguably not by too much. Next, we're going to need the potential energy for our spring. Like the 1D case, all the potential energy of the system is stored in the spring itself. Aside from being in 3D, the big difference between our new setup and the previous one-dimensional setup is the non-zero rest length of the spring. We need to encode this into the potential energy function somehow. To do this, we will directly construct a potential energy for the spring. This is in contrast to the more roundabout approach we took in video 1. Before we dive in to constructing the potential energy function, let's ask what some criteria are for the potential energy function of a purely elastic object. Perhaps most obviously, for an elastic object, when all the external forces are removed, so if the object were just floating in space, it should return to its undeformed or rest state. In our case, this means that the rest length of our spring should be a minimum of the potential energy. Secondly, the energy should be invariant to rigid motion. This means translations and rotations of the whole object. Finally, for a purely elastic object, we are going to assume that the energy depends only on the instantaneous positional configuration of the system. To be clear, depending on the type of object or material we are modeling, we might have different criteria, but these will work well for our spring. Okay, up until now, I've been using this fancy picture to visualize our spring. In actual fact, we are going to represent it as something much simpler. A line that connects the center of our two particles. The initial length of this line will be L0, and will keep the same generalized coordinates and velocities. We're going to start building our potential energy function by defining what's called a strain, a measure of how far the spring has deformed from its reference configuration, its undeformed configuration. A reasonably good strain for a spring is the difference between the current deformed length of the spring and the undeformed length. Note that this strain measure is 0 if and only if the spring length and original length are 0. Now, this goes a long way to satisfying our first criteria for a potential energy. Lengths are also unchanged by rigid motions, so this is already going to satisfy our second criteria. Finally, the length of the spring only depends on the instantaneous positions of the endpoint particles, satisfying criteria 3. The only problem is that L equal to L0 is not a minimum of this function. That can be easily fixed by setting the potential energy to be the squared strain. And we're going to introduce the stiffness parameter K, which, just like in the 1D case, allows us to control how readily the spring responds to external forces. Now we have the final piece of the puzzle. L equals L0 is now clearly the global minimum of this function. In order to define the length, we can look at the vector that points from particle 0 towards particle 1. We're going to call this vector delta x. We can define this vector in terms of our generalized coordinate q by introducing the matrix B, which we make by concatenating 3x3 identity matrices, denoted by I. Now we can use this formula to get a simple compact formula for the length in terms of q. And that looks like this. The length of the spring at any point in time is given by the square root of the magnitude of delta x squared and then via direct substitution we can express this length in terms of the generalized coordinate. Now we take this formula for the length, substitute it directly into our potential energy, and we arrive at the following formula, which gives us exactly what we need. Okay, so again, that wasn't that bad. Arguably, directly constructing the potential energy is easier than the force-based approach we used in Lecture 1. And we've now got everything that we need to construct the Lagrangian for our spring. The Lagrangian looks like this when we substitute in our previously defined kinetic and potential energies. Now we can move forward with deriving the equations of motion, which come from the Euler-Lagrange equation. Our goal here is just to plug everything into this equation and evaluate the appropriate derivatives. But before we do that, let's do a quick simplification. I want you to notice that the only part of the Lagrangian that depends on Q is the potential energy. This means we can rewrite the Euler-Lagrange equations in the following form. Here, we give the negative gradient of the potential energy, this term on the right-hand side, a special name. We call it the generalized forces. It is the forcing term that drives the dynamics in the space of generalized coordinates. We'll denote this vector as a bold-faced F when convenient. While it's a fun exercise to compute these gradients by hand, in practice we often use symbolic math software to do this for us. If you'd like to see a demonstration of this, there's a link in the video description showing how to use MATLAB's symbolic toolbox to do just that. Having essentially punted the right-hand side derivation to computer software, we are free to focus on the left-hand side term. This is somewhat easier to derive, so we'll just do it by hand. We proceed via direct substitution of the kinetic energy into the left-hand side of the Euler-Lagrange equation. Next, we compute the gradient with respect to q dot, and this is made easier by the fact that the energy is quadratic in the generalized velocities. Finally, we take our time derivative, as usual exploiting the fact that the mass matrix is constant. And after all that, we end up with our equations of motion for our spring. Of course, to generate a simulation, we need to integrate these equations in time. However, before we discuss time integration, let's see how we move from a single 3D spring to a bunny's worth. We're going to represent our mass spring bunny as a collection of vertices connected by edges. We can use these geometric objects to represent physical masses and springs. Concretely, we will place a mass particle at each vertex of our bunny and a spring at each edge. Next, we're going to retrace our steps in order to derive the equations of motion for our bunny. We'll see that having done the legwork for a single spring is going to make our lives much easier when it comes to ensembles of springs shaped like rabbits, or any other animal for that matter. As is becoming the norm, our initial step is to define our generalized coordinates. Recall that for a single spring, our generalized coordinate q was the stacked vector of particle positions, as shown here. Perhaps unsurprisingly, the generalized coordinate for our bunny is the stacked vector of all vertex positions. Because each position is 3D and is thus a 3x1 vector, the total size of q is 3 times n, where n is the number of vertices. We can get generalized velocities by taking the time derivative of our very large q vector. Unsurprisingly, this results in q dot being the stacked vector of per vertex velocity values. So far, not much has changed. Just the size of our generalized coordinates has expanded. Let's see if that continues when we talk about the kinetic energy of our system. And the similarities continue. The total kinetic energy of the bunny is the sum of all the kinetic energies of the individual particles. Again, we can condense this sum using our generalized velocity vector by introducing the mass matrix M for the entire bunny. And here, the mass matrix is again a block diagonal matrix, but it's rather bigger than before. It's a 3n by 3n block diagonal matrix with 3 by 3 individual particle mass matrices along the diagonal. Analogously to the kinetic energy, we can define the potential energy of the entire bunny as the sum of potential energies of individual springs. Here, m is the number of springs, and v subscript j are the individual potential energies for each spring. Each v subscript j is computed using the formula for a single spring from earlier in the video. X sub a and x sub b are the positions of the endpoints of the jth spring. The actual values for these endpoints are stored in our large Q vector, and now our goal is to establish a mapping so that we can express the total potential energy in terms of this larger vector Q. In order to do this, we are going to need to introduce the concept selection matrices. To start, let's set the scene by reviewing what happens when we multiply a short and wide matrix with a column vector. What we get is the sum of each little submatrix multiplied by a portion of this larger vector. For our 3D points, if our submatrices, the A's on this slide, are 3 by 3 matrices, each matrix will multiply an individual particle position from our bunny. We can use this to select the ith point in the vector by setting all the A's equal to 0 except for the A in the ith position. Setting this value to identity will, as our summation shows, perform the desired selection. As an example, we can select the second particle position, x sub 1, using the selection matrix S1, which is filled with zeros except at the second position where it features a 3 by 3 identity matrix. Okay, with selection matrices in hand, we can return to our potential energy derivation. So let's do it. The key observation is that we can compute x sub a and x sub b by just selecting them from our giant Q vector. We can formalize this using selection matrices to pick the correct vectors from Q. We need to select 2 points from Q to construct the generalized coordinates for the jth spring, denoted Q sub j. We will denote this endpoint selection matrix E sub j, and it's just the stacked up set of selection matrices for each endpoint. Now we can replace the endpoint positions with our per spring generalized coordinate Q sub j, which is clearly a function of Q. And finally, we can make this relationship explicit, which gives us the final form of the potential energy with which we will continue. So, we've got kinetic energy, and we've got a potential energy, which means it's time, once again, to build a Lagrangian. Done and done. And it's looking pretty similar to what we had for a single spring. The major difference is this summation in the potential energy term. And we're going to spend some time looking at how to deal with that in a minute. And we continue with our greatest hits. The Euler-Lagrange equation returns. Again, we'll discuss computing the generalized forces in a bit more detail later on, but to get started, let's work on the left-hand side here. Now, no one is going to blame you if you are starting to have a feeling of déjà vu. Once again, we're going to start with our quadratic kinetic energy, compute the derivative with respect to q dot. Finally, we take the time derivative, again exploiting the fact that the mass matrix M is constant. And we end up with what by now should be a very familiar term. Putting it all together, we end up at the equations of motion for our bunny, which oddly look identical to those for a single spring. Remember, they aren't really identical. The bunny mass matrix M and generalized coordinate vector Q are much larger. However, The similarity of the formulas highlights an advantage of our approach. As long as we can figure out how to build these operators, things like mass matrices, we can often just skip straight to the equations of motion. But we aren't quite done yet. We know that our bunny potential energy is more complicated than our single spring potential. Let's examine the implications of that. While you could directly try to compute the generalized forces from the bunny potential energy, we can be a little bit smarter about it and make our lives a little bit easier. Due to the linearity of the gradient operator, the gradient of a sum is equal to the sum of the gradients. Differentiating the per spring potential energy with respect to the generalized coordinates gives us a more useful formula which expresses the generalized forces using a sum over all of our springs. A little more rearranging allows us to see that the generalized force for the bunny is computed by summing up the generalized forces acting on each spring. But what is the transpose of our edge selection matrix doing? Well, we know that multiplying by the selection matrix selects a small subset of our larger Q vector to build Qj. Conversely, multiplying by the transpose distributes a small per spring vector back into our global force vector. Here we see one example for the labeled spring. We compute the generalized force F sub j, which is just the stacked vector of three-dimensional forces acting on the endpoints of the spring. Multiplication by E sub j transpose places those forces in the appropriate positions in our global force vector. In this case, those are the second and the last position. The summation tells us we need to accumulate forces from all the springs acting on these nodes. This process of distribution and addition is called assembly because we assemble a global force vector from the force vectors of individual springs. Assembly is the final piece of the puzzle required to evaluate all the terms in our equations of motion. This means it's finally time to move to time integration. To generate bunny animations, such as these, we are going to use a popular time integration scheme in graphics, the linearly implicit time integration scheme. This is going to be a simplification of the backwards Euler scheme we learned about in the previous video. Alright, here are our equations of motion for the bunny. Let's start building our time integrator. We take a backward Euler time integration scheme as a starting point. Unfortunately, our bunny potential energy is nonlinear, so we aren't going to get a nice update formula like we did for our linear 1D spring. Instead, we're going to build a simple approximation. We start by substituting our position update into our velocity update equation. Next, we build a first-order approximation using the Taylor expansion of the force around the current configuration Q at t. Here, we see the appearance of the gradient of the force with respect to the generalized coordinate. This term is called the stiffness matrix. Now be very careful, this should not be confused with the stiffness parameter, which controls how readily the spring deforms when subjected to an external force. We're going to call this stiffness matrix K, potentially adding to the confusion, but unfortunately or fortunately, these are the agreed upon terms in the literature. Just like with our previous backward Euler derivation, we end up with updated Q dots on both sides of this equation. Collecting terms yields our update equation for Q dot and then for Q itself. Note that updating involves solving a linear system at every time step of the simulation. Because our update is derived from a linear approximation to a fully implicit integrator, we call it linearly implicit. An important aspect in implementing this time integrator is understanding how to build our new stiffness matrix term. So let's have a look at how to do that next. We start with the definition of the stiffness matrix and the generalized forces. And from this, we can see that the stiffness matrix is really the negative Hessian, the matrix of second derivatives of the potential energy. Just as before, we can move our derivative operation inside the sum and work on a per spring basis, rather than forcing ourselves to work on the whole mesh at once. And this is very convenient. Judicious evaluation of this second derivative gives us something analogous to our generalized force computation, except here we have a per spring Hessian sandwiched between our per spring selection matrices. We can simplify this a bit more by introducing the per spring stiffness K sub j, which clearly illustrates that our global stiffness matrix K is assembled from these per element K sub j stiffness matrices. Let's take a look at an example to make this a bit more clear. Just like with our generalized forces, assembly of the stiffness matrix occurs by visiting one spring at a time. The per spring stiffness matrix, K sub j, is a 6x6 matrix made of 4 3x3 blocks. Each block describes a relationship between two of the endpoints of the spring. Our selection matrix sandwich takes each block and places it in the global stiffness matrix at the row and column indices associated with the spring endpoints A and B. In this case, the spring endpoints are vertex A, which corresponds to index 0 in our Q vector, and vertex B, which corresponds to the last index. We sum K sub AA into the upper left block of the global stiffness matrix, K sub BB into the lower right block, and K sub AB and K sub AB transpose into the 0n and n0 blocks respectively. Repeating this procedure for each spring in our bunny assembles the stiffness matrix. Once we've done this, we can execute our linearly implicit time integrator to animate this wiggly bunny. And this is pretty good, but there's one more thing we need to talk about before we are done. You might have noticed that the bunny is not flying all over the scene as we interact with it. That's because it is secretly glued to an invisible floor. I want to end by discussing how to implement these invisible constraints. Imagine we know that the ith vertex of our bunny mesh is fixed to the floor. This means that its position, x sub I, is always going to be equal to some constant value, b sub I. We are going to enforce these constraints using selection matrices. To do this, we're going to introduce a new variable q hat. Q hat contains the non-fixed generalized coordinates, the vertex positions that are allowed to move. We can build P, which will select these non-fixed points from the full vector of generalized coordinates, Q. From our discussions on assembly, we know that multiplying by the transpose of a selection matrix assigns values from a compact vector to a larger vector. In this case, multiplying Q hat by P transpose builds a vector that looks exactly like our original vector of generalized coordinates, but has zeros in the positions assigned to fixed vertices. To fill in these gaps, we're going to introduce a constant vector b, which is full of zeros, but contains the constant fixed vertex positions for the ith entries. We can use the sum of P transpose Q hat and B to build generalized coordinates Q. And by definition now, certain points in this Q vector cannot move. And this is exactly what we want. From this definition of Q, we can compute Q dot by differentiating with respect to time. Now remember that b is a constant vector, so b dot is 0, and so it simply goes away. Finally, we need to build these constraints into our time integration scheme. Direct substitution of our formulas for q and q dot gives us the following new update equations. Here we're going to use the selection matrix P to project out equations related to fixed points in the mesh. Now we can compute the velocity of the non-fixed points, the points that are allowed to move, via q hat dot, and then use this to recompute an updated full q. Now we can finally generate our animation, which looks like this. And that's really the last piece of the pie required to generate this wiggly 3D bunny. Now, we covered a lot in this lecture, but these concepts are going to come up again and again. In fact, next week, we're going to reuse them when we hit the big time, which is learning about the gold standard method for generating physically based animations of Elastica, the finite element method. So with that, we reach the end of our journey. I want to say thanks for watching, and hopefully I'll see you next time.